Okay, in our last section, we introduced the derivative as the limit as h goes to 0, but we were dealing with the derivative at a x value equal to a. I'm going to now introduce that the derivative itself can be represented as a function, not just a value, but a function. So let's take a look at an example. Let's let f of x equal x squared. Then, according to the definition I just gave you, we would have f prime of x equals the limit as h goes to 0 of f of x plus h, which looks like this. I replace x with x plus h in my function, minus f of x, which is x squared, all over h. Now, what I'd like to do is simplify and expand this on the top, giving us x squared plus 2hx plus h squared minus x squared. So this was just this, expanded out, and of course all of it over h. Now, notice I have a positive and a negative x squared which eliminate each other. So now we have 2hx plus h squared all over h, and the numerator is factorable. So I shall factor it, taking out the greatest common factor, which is h. Notice I have an h on top and bottom that can reduce out, technically giving us a different function, but it's equal everywhere except for possibly at h equals 0. So I now have an object where I can use direct substitution, and I will come up with my final answer by plugging in 0 for h. So I now have taken the derivative not at a point, but I have taken the derivative of the function and come up with a derivative function. Let's see what that means, a derivative function. So I'm going to take a look at the graph of my original function. Let me color code this. Let me just slide this over. Okay, so the original function and I'm going to make a quick graph. And just making a rough graph of my function f of x. Okay, we should know what x squared looks like. Y equals x squared, the graph. Let's just take a couple of points. If I was to look at possibly, let's see, let's go with about right here. I'm going to say -1 for y is going to produce 1. I'm sorry, -1 for x will produce 1 for y. So I'm at this point, -1, 1. If I was just to draw an idea of what the tangent line looked like there, which I'll do it in green, it looks something like that, rough graph. And the slope of this tangent line is clearly negative. According to what I just calculated, and let's do one more. Well, that's good enough. So I can give you some information now. Let's see. F of negative 1 was 1, so I have a point. And now, according to this formula, I could find the slope of the tangent line at this point simply by plugging it into my derivative formula. One of the things you should always do is think to yourself, does this answer make sense? So what I just said is that the tangent line at negative 1, 1 of the function f of x has a slope of negative 2. That is my instantaneous rate of change of this tangent line at that point, negative 1, 1. And I was able to find it by a formula. Every single point now, I could find the instantaneous rate of change. I can find how fast the function is going up or down without having to recalculate the limit for each point, but just by having it one time. So now that we know this information, that given f of x equals x squared, f prime of x equals 2x, I can find the tangent line for any point on the function. So let's say I wanted to calculate a tangent line on the function that had a point at 3, and if I plug in 3 and square it, I get 9. So here's my point, and the slope of my tangent line will equal the derivative at 3 . So now I have a slope and a point. I can put it directly in point-slope form. And that's the equation of my tangent line in point-slope form. If I want to simplify it, I can put it in slope-intercept. And again, for each and every point on the function, I can use my derivative function now to find the instantaneous rate of change at any location.